The problems we've looked at so far either had no boundaries, like propagating waves in free space, or had the rather idealized boundary of an infinitely high vertical wall. Of course, we need to be able to handle the more realistic situation of barriers of some finite height. To do so, we need to have boundary conditions that tell us how to handle the wave function at such finite height barriers. What we will do now is set up reasonable boundary conditions on both the wave function amplitude, how high it is, and also its derivative, its slope.
So let's look at these boundary conditions then. For our Schrödinger equation here, let's presume that the energies we're going to get solutions for are finite energies, that the potential is something that is finite, and that the wave function is something that is finite. We certainly want the wave function to be finite, otherwise we're going to get infinite probabilities somewhere in our results. Then, if everything else here is finite, this second derivative has to be finite. Otherwise, we would have something infinite here being equal to something finite over here. So, the first derivative, d psi by dz, must be continuous. If there was a jump in d psi by dz, then the rate of change of d psi by dz would be infinite at that point. That is, the second derivative would be infinite. Therefore, we require, because of these assumptions of finiteness, that the first derivative, d psi by dz, must be a continuous function. That is, one with no jumps, no sudden jumps in it. Also, d psi by dz must itself be finite. Otherwise, d2 psi by dz squared could be infinite. If this was not a finite function, it could be an infinite result that we would get for the second derivative, because it's the limit of a difference then involving infinite quantities. So, in order to be sure that d2 psi by dz squared is not infinite, we need to require also that d psi by dz is a finite quantity at all times, all positions. For d psi by dz itself to be finite, then that means that similarly psi must be a continuous function. If psi had had a jump in it, then that would be a problem. So now that we have these two boundary conditions, psi must be continuous and d psi by dz must be continuous, we can proceed to solve problems with finite heights of boundaries.
When we think of a classical particle, such as some ball, we might imagine, reaching a finite potential barrier or a wall, it will typically reflect off the wall. The ball would just bounce off the wall, even if the kinetic energy of the ball is more than the potential energy it would need to have to get over the top of the wall. If the barrier is a slope, the ball can continue over the barrier if its initial kinetic energy exceeds the amount of the potential energy that corresponds to the height of the barrier. So a ball coming in here could roll along, roll up the slope, and keep on going. However, the ball could not get to the other side of the barrier if its kinetic energy was less than the barrier height, considering the barrier height as the potential energy. And certainly, the ball could never be found inside the barrier. A quantum mechanical particle, however, can be found within the barrier and can get to the other side of the barrier even if its energy is less than the height of the potential barrier. This is the quantum mechanical phenomenon known as tunneling. It might seem a very strange behavior, but with the physics and the mathematics we have set up now for Schrödinger's equation, we can actually solve this problem and understand this behavior quite easily.
So let's look then at the case of an infinitely thick barrier. We presume we've got a barrier of height v0, and the potential is 0 to the left here. So we've got an energy going upwards and 0 potential here, v0 potential everywhere to the right, going off as far as we like in the z direction. And the barrier is at position z equals 0. So a quantum mechanical wave, we imagine, is incident from the left. The energy associated with this wave is going to be E, a positive number, so greater than 0. we are going to allow for the possibility that even though we've got an instant wave here, there might be some reflected wave into the region on the left. And we're going to use the general solution of the equation on the left. We're going to use complex exponential waves, so the general solution could be written this way: c times e to the ikz plus d times e to the minus ikz. And as usual, k here is the square root of 2me over h bar squared, because that's the energy in here and the potential is 0. Now, c e to the ikz is the instant wave, and we think of it as a right-going wave. And d e to the minus ikz is the reflected wave going to the left. We're going to presume that we've chosen our energy E so that it's less than V0, so it's somewhere in here. So the incident wave energy is less than the barrier height. Now, inside the barrier then, we have our Schrödinger equation as before, but this V0 is now a constant, and incidentally, it's greater than E, the energy of the instant wave. So we can rewrite this mathematically as d2 psi by dz squared is equal to all of this stuff on the right here, and V0 minus E is a positive number. The general solution of this wave equation for the wave on the right is something that we could write in this form. Note that we have real exponents now in our exponentials because this is a positive number, and you can check that this is indeed a solution of the equation up here. And now we have a kappa in these expressions, and kappa is the square root of 2m V0 minus E over h bar squared. Remember, this is a positive quantity, so kappa is a real number here. We presume that this number, f, is 0. Why do we presume that? Because otherwise we would have an exponentially growing wave on the right, and it would keep on growing forever. And that's kind of unphysical. It would mean that the particle was never found anywhere over here. The particle would always be found arbitrarily far to the right. So we discard that one. In other words, we set f equals 0. We say that's unrealistic, unphysical for this situation. So we're left with this term, which of course corresponds to an exponentially decaying wave. So the wave on the right, inside the barrier, is now going to be just some constant g we're going to figure out, times e to the minus kappa z. That's exponentially decaying, with our kappa, as we said before. So, importantly, this solution proposes that the wave inside the barrier is not 0. Instead, it falls off exponentially. This is not like classical physics. So, using our boundary conditions then, we can complete the solution here. On the left, we have this wave here. It's a sum of a forward propagating wave and a backward propagating wave with coefficients to be determined. On the right, we have only a decaying exponential with a coefficient to be determined. And these k's and kappas are dependent on what energy we're working with. Continuity of the wave function at z equals 0 is going to give us this equation here. In other words, if you put z equal to 0 in here and z equal to 0 in here, then psi left of 0 is just c plus d, because e to the I0 or e to the 0 is just 1. And on the right, similarly, if we put z equals 0, the exponential just becomes 1. So on the right, the wave function is just g at z equals 0. So we've got c plus d is equal to g. Continuity of the wave function derivative gives us this relation here. We can work that out by taking the derivative of this wave function here. That is the derivative of each of these terms. The derivative of this term here gives us an ik out the front. The derivative of this term gives us a minus ik out the front. And we're setting z equal to 0 now, so the exponential e to the ikz and the exponential e to the minus ikz, of course, are just 1 in that case. So the derivative of this wave function at z equal to 0 is ikc minus ikd. Similarly, on the right, taking the derivative of this wave function, we get minus kappa times the wave function. evaluating that at z equals 0, where the exponential just becomes 1, gives us minus kappa g for the derivative on the right-hand side of the barrier at z equals 0. So we said the derivatives have to be continuous, so these two have to equal one another. We can rearrange this if we want to, and get c minus d is equal to I kappa over k times g. So we can add these two equations we just found together. So we add the left-hand sides and we add the right-hand sides here. Adding the left-hand sides, well, the two c's add, but the two d's cancel. So adding the left-hand sides here gives us 2c. Adding the right-hand side gives us 1 times g, that's this one, plus I kappa over k times g. I can rearrange that if we want to. Multiplying by k on the top line here gives us k plus I kappa over k times g. Equivalently, we can rearrange this. In other words, we can get g in terms of c. In this problem, actually, we'll never have to decide exactly what c is, but we do want to know all the other constants in terms of one of them, so we can find g in terms of c. We could rearrange that if you like to get the complex stuff on the top line and real numbers on the bottom, but actually we'll use this form. So now we have found what the amplitude g is in terms of the incident amplitude c. We know how to relate the amplitude of the wave inside the barrier to the amplitude of the incident wave. Similarly, we can subtract this equation from this one. These are two equations we got from our boundary conditions. Subtracting this from this, well, the c's now cancel and we get 2d on the left-hand side. And subtracting this from this, we get 1 minus I kappa over k times g, which we can rearrange if we want into this form. So we already found that g was equal to 2k over k plus I kappa times c. Then we now have, substituting that into here, that d is equal to k minus I kappa over k plus I kappa times c. So we found the amplitude d of the reflected wave in terms of the amplitude c of the incident wave. So we've now formally solved this problem. The wave on the left is a forward propagating wave of amplitude c and a backward propagating wave of amplitude d. We know what d is in terms of c. And the wave on the right was our decaying exponential, and we know what g is in terms of c. And we know, of course, the k and the kappa. So these are the solutions. We don't need to specify what c is. We're really just interested in the relative amplitudes and so on of all of these waves. So incidentally, note that we figured this out. D is equal to k minus I kappa over k plus I kappa times c. So d over c, trivially, is just k minus I kappa over k plus I kappa. So if I take the modulus squared of this, I multiply this by its complex conjugate. Well, this is its complex conjugate. But you'll notice that these just cancel, so this is 1. That means that the barrier is 100% reflecting. So the amplitude of the wave going in and the amplitude of the wave being reflected are both of the same magnitude. Though there is a phase shift on reflection. This is not a real number. This is a complex number. This is a complex number here. This is a complex number here. That means the wave is reflected with a phase that is not 0 or pi. And this effect has no classical analog. Let's plot the real part of the wave function here as an illustration. And we're going to take an electron of energy 1 electron volt and a barrier of height 2 electron volts. And here's what that wave function would look like. So we're seeing on the left we have this sinusoidal-like real part here, or cosinusoidal part. And we have our exponentially decaying part in there. Note that the wave function and its derivative are both continuous. So the height of the red line and the height of the blue line are the same at this interface. And also you can see the slope just goes straight through here. Note that there is a phase change on reflection. This wave here doesn't hit 0 or it doesn't hit 1 at this interface. It's some other phase that we're seeing here in this wave.
Note the exponential decay of the wave function into the barrier. Because of that, there must actually be a probability of finding the particle inside the barrier. As I said, this kind of behavior is sometimes called tunneling or tunneling penetration, by some loose analogy with the classical idea of digging a tunnel out of a barrier here. There is, however, no mathematical connection between the classical idea of a tunnel and this quantum mechanical process. This is one of those quantum mechanical ideas that really has no analog in classical mechanics. We should say, though, that this kind of exponential penetration is actually quite common in classical waves. It's not something that you would notice much in everyday life with light waves, because when it occurs for light waves, these penetration depths are quite small. It occurs everywhere, though, that you have something that is called total internal reflection. If you're a good swimmer, then you may know that if you open your eyes when you're swimming underwater and you look up, for most angles far from the vertical, the surface of the water looks entirely reflecting. This is a well-known and well-understood phenomenon with light, and it's the reason why also we can guide light in optical fibers over gigantic distances. The light will bounce up and down inside them. If you looked very closely at the light, however, you would find that the light penetrates exponentially into the air for a very small distance above the water surface. So the light coming up to the water surface, yes, it's reflected, but it actually penetrates a very small distance into the air above the water surface. Now, while that penetration is practically negligible for reflection of what you see off the water-air interface, it's actually very important in the physics of optical fibers that we use for telecommunications. The core of those fibers is only something like 10 microns in diameter. That's about 1/10 of the diameter of a human hair. And these exponential penetrations, as the light reflects off the internal surface of these fiber cores, are actually very important in understanding the behavior of light in the fibers. So, for wave mechanics in general, such exponentially decaying penetration is not at all uncommon. It's just that, again, we were not expecting to see this with matter. But because we have wave behavior of particles like electrons, we can see this exponential or tunneling penetration with electrons too.
So let's look at some orders of magnitude here of the sizes that are involved in this tunneling penetration. If we take a barrier of height 2 electron volts and an incident electron energy of 1 electron volt, then our kappa we can calculate from this formula here. So let's look at what that gives. We have 2 times the mass of the electron here. The rest mass of the electron is about 9.1 times 10 to the minus 31 kilograms. Our potential barrier height V0 was 2 electron volts. Our energy of the incident electron was 1. Because these are in electron volts, we have to multiply them by 1.602 or thereabouts times 10 to the minus 19 to get the energy in joules. And then this H bar here is 1.055 or so times 10 to the minus 34 joule seconds. We have to square that. So this is what we have to calculate here. And the answer to that is 5 times 10 to the 9 per meter, or meters to the minus 1. That means that the attenuation length, as it were, of the wave amplitude into the barrier, that is, the length to fall to 1 over e of its initial value, is about 0.2 nanometers, or about 2 angstroms. We can look at that on our diagram here, our graph. The exponential decay length here of about 0.2 nanometers is this distance in here, and you see it corresponds to the fall off of the wave function by about a factor of 1 over e. Note that as we increase the energy here, we're going to see that the exponential decay gets longer. So we're going to look at an animation here. This particular calculation here is for the energy 0.15 electron volts. We still have our 2 electron volt high barrier. And we can look at what happens to this wave as we let that energy increase. So we're repeating the calculation for a bunch of energies, and we're plotting them up here as an animation. So see that now that we're very near to the top of the barrier, the energy is 1.95 electron volts and the barrier height is 2 electron volts, we have a very long exponential decay of the wave function here. And let's look at that again. We see this exponential decay getting longer and longer, especially as we get very near to the top of the barrier here. And note also there's a change in the phase shift. Here, the wave is nearly reflecting with 0 phase change. Not quite exactly, but nearly 0 phase change, because that gives a peak at the reflection point. And let's look again, this time watching the phase of the reflected wave. So you see that the phase is progressively rising up towards being essentially 0 phase change on reflection, but initially it started out at quite a substantial phase change on reflection. Let's look at that again. See, there's a lot of phase change on reflection here. Now, that was the real part of the wave function we were looking at. It's probably better to plot probability densities. The wave functions are not of absolutely clear meaning, but probability densities are. Anyway, it was quite difficult to think about plotting a complex wave, which is what we should have plotted. But the probability density is very meaningful, so let's look at that. So our probability density inside the barrier is going to be proportional to psi right of z, all squared. So given that psi right itself is e to the minus kappa z, then psi right squared is e to the minus 2 kappa z. And here's a plot of the probability density in this problem. Now, there are several interesting things about this. First of all, we have our exponential decay, and we'll look at just how rapid that is in a moment. Note also that we have a standing wave to the left. Now, this standing wave of probability density actually goes exactly to 0 at these points. And it does that because we have 100% reflection. And 100% reflection in a standing wave pattern gives you zeros in the standing wave. So there is actually no probability of finding the particle at these points. So we're falling by 1 over e here in about 0.1 nanometers or 1 angstrom, because we're now falling at e to the minus 2 kappa z. And this is a favorite trick of quantum mechanics professors in setting exam questions, is to trick the students who will give you the answer for this decay length and not this decay length here when we talk about probability densities. So let's look at an animation again here of the probability density at a barrier. Again, we're starting out at a very low energy, 0.15 electron volts. You see that the probability density is falling off quite fast in here. Also, you see that we're nearly, but not quite, at a 0 here in this standing wave pattern. The reflection of this barrier here is nearly 180 degrees out of phase. Actually, to make it 180 degrees out of phase, this barrier would have to be infinitely high. So we're close to, but not exactly at, a 0 in the reflection here. So that means we're getting nearly 180 degrees phase shift on reflection. And then as we let the energy go up, we'll see this tail get longer, especially as we get up to the top, near the top of the barrier. And we'll see this phase change also change accordingly. As we increase the energy here, as we said, the exponential decay gets longer. And let's look at that again. Noting this time the phase shift, we've seen the exponential decay get longer. Let's look at the phase shift this time. So progressively, we're moving towards getting nearly 0 phase change in reflection from something rather close to 180 degrees phase change in reflection at the lower energies.
So now we've set up our wave mathematics carefully for particles hitting barriers. And out of that mathematics has come this strange phenomenon of the tunneling penetration into the barrier. As I said, this kind of exponential penetration of waves is actually well known for classical waves. The surprise, like many of our other surprises in quantum mechanics, comes from our proposal that electrons and other particles with mass must also behave like waves. Now that we've set up this understanding of what happens when particles encounter these finite barriers, we can go on to solve some more realistic quantum mechanical problems, and that will be the topic of our next lesson.